This video is to introduce Lab 1 of Chapter 6. It may not be necessary. You can do many of the commands on your own, but if you do need some help, feel free to watch this video and pause it as needed. So we'll begin by looking at the graph for the area between the two curves. If we press enter on this line and simply plot it, Maple doesn't plot as well when you use the y equals command, and if you just right click and do a 2D implicit plot, it doesn't choose a very good window. Now you could edit that by right clicking, go to Axes and Properties and edit the window. If you right click and plot and go to Plot Builder, you're able to plot it. It chooses a better window, and if you look at the preview, it's also not very good. It's not plotting enough points. So the better choice of these would be to simply copy and paste it without the y equals and go to Plot Builder. So we'll do that. We'll copy it, go to a blank math line, paste it, take out the y equals, right click, Plots, Plot Builder, and we can choose the window we would like. 2D plot is correct. It's not a very big window that we need, so -5 to 5 might be good. And under options, we can go to the y values and do something similar like -5 to 5. You can preview it if you'd like. I believe this should be a good graph. And it's smoother. Notice they're intersecting somewhere around 1. We'd like to find that point of intersection and get the area in between the two curves. The blue one is the x to the 5th minus x. So these again are inappropriate graphs. It should be a smooth curve with a reasonable screen. If we wish to now go on and do the calculus, we want to find where they intersect. So if we again copy and paste, we can change that comma sign into an equals, right click and solve. If we solve it for the variable x, it's going to give us an ugly answer. One of the solutions is x. We're better off right clicking and solving from numerically from a point it's near 1, and we click OK. Now that ends up being the best choice for the limits of integration. So let me scroll down. We put together the integral, paste in the approximate point of intersection as the upper limit, and of course we get the area between the curves. You may wish to pause at this point and carry out those steps. If not, you can continue on. We next want to look at the graph of a parametric. Recall that when you put them in square brackets, the x equals and the y equals expressions, you can choose Plot Builder. I'll go ahead and repeat this process. Go to Plots, Plot Builder. The first one that comes up is a 2D parametric plot. And it turns out that the t-values of -3 to 3 are not too bad. I won't regraph, but this is what it looks like. It's a loop that encloses itself. We'd like to take some time to find out what the area is for that loop. You may have forgotten that we need to get the limits for integration, and that means we need to solve for t. Set up the y and the derivative of x. Now this is one where the x expression is obviously quite easy, so the derivative is 2t. And the y expression you can copy and paste into an integral and create the expression t cubed minus 3t times 2t's, the y and the derivative of the x. Notice that I put in the square root of 3 to negative square root of 3 as limits of integration, and we have the exact area of that loop. Next, we want to look at 36. Again, if you wish to pause and carry out that previous step, that's fine. Otherwise, continue on. We'll look at the graph of the asteroid. In order to get the graph, we're going to simply use the number 2 in place of the letter A. That controls the size of the asteroid. And so it's a cube at the end. We again plot in parametric using Plot Builder and choose 2D parametric. The window it chooses is nice. We see the curve. We'd like to get the area of this. Now, it makes sense to use the symmetry from 0 to pi over 2 and then just take that area times 4. Once again, we do the same process, y times the derivative of x. So we could copy paste that in if you'd like, and then of course we need to go get the derivative. And when you right click on the x expression, you can say differentiate with respect to theta, and we can assemble the integral. Notice that you actually want to integrate from pi over 2 to 0. It's okay if you go from 0 to pi over 2, however it ends up negative. So the direction in which you integrate affects whether or not it's positive or negative when integrating in parametric. Once again, you can pause if you wish to carry out those steps. Otherwise, we'll continue to the arc length problem. From 6.4, very first thing we want to do is right click and plot that. You can assemble the pieces in square brackets. Notice that we want to use 4 times pi. You could type capital P, small letter I in the window for plotting, and we get this spiral shape. We'd like to know what the arc length is, so we set up the appropriate integral from 0 to 4 pi. We do want the derivative of x and the derivative of y, so I simply copied x and differentiated, copied y and differentiated, put them together inside the integral. Notice it gives us an answer in terms of a function, and so if we right click we can approximate it. Finally, if you have time, you can use this link to go look at the Cornu spiral. I also pasted into the cloud a document that if you press enter on it, it will create the spiral, and you may view the video at the website.